area. For homework number 11, problem number 21. If I go to sketch the graph of this function, when I go to graph 1 minus y squared, that is an x equals negative y squared with a vertex at the origin opening left, and it is then moved right 1 unit. The other graph is an x equals y squared. X equals y squared opens to the right with its vertex at the origin, and this minus 1 is telling us to move left 1 unit. And they intersect right there on the x-axis. Now, I have two choices. I can either go the way of my rectangles are those regularly drawn vertical ones with teensy tiny horizontal widths. That's not going to be pleasant. Or I can go the other direction. And I'm going to redraw these real quick. If I go the other direction, then the right side of the rectangle is going to follow the green function. The left side is going to follow the red function. And this is going to be a nicer integral to set up. If I force myself to go with these kinds of rectangles, I am going to have to isolate these y values in terms of x, and then I'm going to end up getting a positive root and a negative root when it comes to solving for y in terms of x. The positive root is when you are having a positive y, which would be the above the x-axis parts. The negative root would be when your y is negative and you have the under the x-axis parts. So what you actually have to do is, with the red function, top y value, which is a positive root, minus negative y value, which is a negative root. Then you have to change at x equals 0, start a new integral, and do the same thing with the green function. Really not the best way to go. And let me make sure you are clear that if you draw your rectangles in the way we did in chapter 5, where it's a vertical length, the tiny cuts are horizontal, and that's why those end up being dx's with the integral. When you draw rectangles that have their length horizontal and their tiny cuts vertical, those tiny cuts are a change in y, so that's where you get your dy integral. So when you are horizontal, it's an integral with respect to y. When it's vertical, it's an integral with respect to x. So I'm dealing with respect to y. That means I need to know the y coordinates of intersection. I can set them equal to each other and solve the system. I will end up getting -1 and +1 for the y values. Now, to get area, all I need is to multiply the length across by the tiny other dimension, dy. That length across is whatever x is equal to on the right side minus whatever x is equal to on the left side. And keep in mind that as we move from y equals -1 up to y equals 1, I am looking at my right x minus my left x as I go along to get these different lengths multiply each of those by a tiny dy, and that turns it into area. So my x right is 1 minus y squared. My left x is y squared minus 1. And that's the integral setup. I'll go ahead and solve the integral for you in case you need to see that. And so that I don't mess up, I'm going to go add the opposites. And I have 1 plus 1 is 2. Negative y squared minus another y squared, 2y squared. When I integrate my constant, I get 2 times the variable. Constant multiple 2 times, use the power rule, add 1 to the exponent and divide by that exponent. Plug in the 1, minus plug in the negative 1. When I plug in negative 1, I will get a negative 2. This negative 1 cubed will change this subtraction to an addition. And 2/3. So I end up with, I'm going to add the opposites. 2 plus 2 is 4, minus 2/3 minus another 2/3 gives me minus 4/3. And you can simplify the fraction from there. And let's move to the next problem. Number 22. We need to sketch the graph of sine, but it is compressed or stretched horizontally. And if you remember, you look at what is x multiplying by. So I have a pi over 2 being multiplied by my x right in there. When I'm looking at how does it stretch, compress horizontally, I actually take what x is multiplied to and I divide it by that. So a normal period of 2 pi is going to be a period of 2 pi divided by pi over 2, which turns into a period of 4. And just to double check that fraction, what I'm doing is multiplying by the reciprocal, and hopefully there you can see the pi's cancel. These guys are gone, and I have a 4 left over. Then that's a really nice cycle to work with. And then my sine graph does its normal thing of start in the center, go up, middle, bottom, middle. Whee, whee. Then I have y equals x, which is my line that goes through 1, 1, and 0, 0. And we know that when it comes to sine, its high y value is 1, its low y value is negative 1. So I'm trying to find the area in this region. And I get to choose which way I want my rectangles to go. I would say default with drawing them vertically. If you draw vertically, you can see that it is going to follow on the bottom the green function, which is y equals x. On the top, it is going to follow the sine function. And let me draw that in a little bit better because I drew too far out. Yeah, that's going to be a problem. Let me do the undo button instead. There we go. So I'm just drawing a vertical line in between those two functions. With area, I have a length, which is my y top minus my y bottom. My y top is sine of pi x over 2. My y bottom is y equals x. So that gives me length, which is 1 dimension. I multiply it by a little tiny dx, and that takes me to 2 dimensions. And with a dx integral, I need to look at my x values being 0 to 1, and know that that is specifically looking at horizontally existing from 0 to 1. Then to solve my integral, I can do the integration faster than I'm showing you right now, but I'm going to go slow. I can split this integral up over the subtraction. And I'm doing that because I need a u substitution for the first term, but I don't need to use it after the subtraction sign. I can do that one the normal way. So with a u being equal to pi over 2 times x, du dx is pi over 2. That means dx, when I multiply it to the right, is equal to du times 2 over pi when I bring that fraction over to the left side. Then the integral from there is sine u times 2 over pi du. And I need to change the limits on my integral by putting them into the chosen u. So that means when x is equal to 0, plug it in to this x, u is equal to 0. When x is equal to 1, plug it into this x, pi over 2 times 1 gives me pi over 2 for the u. And now I'm not going to go back to x with that one. I'm going to work on the other integral real quick and just bring it down over here. It is staying with respect to x. And now I'm going to integrate. I have constant multiple 2 over pi. The integral of sine u is negative cosine u from u equals 0 to u equals pi over 2. And I'm going to pull this negative sign out with the 2 pi constant. And then I'm just dealing with the cosine function, plugging in the pi over 2, minus plugging in the 0. Cosine of pi over 2 is 0. Cosine of 0 is 1. Negative 2 over pi times negative 1 gives me a positive, whoa, I think I touched something and made it move, gives me a positive 2 over pi. But don't call that the end. I'm going to take that little box off because I've also got this. Minus, and now as I solve the integral of x is x squared over 2. I plug in the 1, minus I plug in the 0, and I ultimately end up getting minus 1/2. So in total, 2 over pi minus 1/2 would be the answer to that area. Okay, number 25. For number 25, I'm going to erase the stuff to the left over here so that I can use that. All right, y equals x squared. Now, I don't expect that you necessarily know what this graph looks like. basically, if you play around with it a bit or even do some calculus on it, what you will find is it has an absolute maximum when x is 0. If you plug 0 into this x, you get y value 2. Now, if you think about it, as x goes to the right or to the left, you're going to get the same answer out. You've got an even function, so it has y-axis symmetry. Also, as x grows from 0 to an absolute value that is larger and larger, that denominator is going to become bigger, and that will cause the fraction to become smaller and smaller and smaller, heading to 0. So basically, it's a bit of a bell curve, like that. Now, we need to know where they intersect each other. So it is symmetric, even though it's not drawn perfect. So I set them equal to each other. X squared is equal to 2 divided by x squared plus 1, and I solve this equation. I multiply the denominator over to the right. That gives me x to the 4th plus x squared, and then subtract the 2 to get 0. Now, this is a quadratic form because you have your middle term is an x squared, and your leading term is an x squared. Because of the squared, it's a quadratic form, which means it's going to factor with x squareds instead of x's. And now two numbers that multiply to make -2 and add to make +1 would be +2 and -1. And that's how they factor. This will never equal 0 because I'm squaring a number and then adding to it. For this one, I'm going to get plus or minus 1. X equals plus or minus 1. So now I know the x coordinates of intersection. And I definitely want to do the regular rectangles, the vertical ones that give me dx. So as I get ready for the integral, I am still finding area. So I have the length, which will be a y top minus a y bottom, times the teensy tiny little horizontal cuts dx. The x's that the region goes between is -1 and 1. And now all I have left is to get into the specifics of the equations to find this length based on which x am I located at as I go from -1 to 1. So the y top is 2 over x squared plus 1 minus the y bottom is x squared. Now all I have to do is integrate. For the first term, you want to recognize that what you have is a constant multiple of 2, and the integral of 1 over x squared plus 1 is inverse tangent or arctangent. Then integrating the second term of x squared, x cubed over 3, and then we are evaluating from -1 to 1. Plugging in the 1, I have 2 times inverse tangent of 1. The answer to an inverse trig function is always an angle, so it's what angle gives me a tangent answer of 1, and that would be pi over 4 within the domain of the angle range that arctangent is allowed to be. And I'm still working on plugging in the 1, so 1/3, minus, and now when I plug in the -1, the arctangent of -1 is asking what angle do I end up getting a tangent value of -1 out. And I have to remember that arctangent only looks at negative pi over 2 to positive pi over 2. Tangent is equal to -1 at negative pi over 4. minus, and then plugging in a negative 1 or negative 1, I will get a negative 1/3. So I'm changing that to a positive. I'm going to let you finish up the arithmetic from there, and I'm going to move on to the next problem, number 32. I need to erase. So with number 2, you are supposed to evaluate this integral who uses absolute value, but you're going to do it by drawing its region and figuring out how to actually set that up into two separate integrals. So I need to draw the graph of y equals, let me color code this, the square root of x plus 2. Let me do a better job circling. And the other y is x, so that I can see the subtraction of those two functions. The square root of x plus 2, when I draw it, it is the square root graph moved left 2 units. And then y equals x is our lovely line that we are used to. And so from x equals 0 to x equals 4 is where the integration is occurring. So 0, I need to know what the intersection point is, and then I need to figure out where 4 is with respect to that. So I need to set the functions equal. When is the square root of x plus 2 equal to x? Square both sides. Make one side 0. Factor x minus 2, x plus 1, and that equals 0 when x is 2 or negative 1. And I need this x coordinate, and that's where x is positive, so it's the positive 2. And if I'm going to 4, that's past that. So I'm going to draw this out a little farther. And that's about 4 right there. And to get the correct region, I want to draw vertical lines in between the two functions. So I already did that here. After I pass the intersection, when I'm drawing vertical lines between the two functions, I get what you see here. And I end right there at 4. So when I go to setting up the integral, I have to set up two integrals. First, from x equals 0 to the intersection point of 2, my top y value minus my bottom y value would be when y is x plus 2 minus when y is x. And because I'm making vertical lengths, the infinitesimally thin dimension is x. Then I'm going to add that to the area that I find when I start at 4, or start at 2 and go all the way to 4. This time the top y value is y equals x, minus the bottom y value is y equals the square root of x plus 2. And I will solve one of these two integrals for you because they're pretty similar. If I solve this one, I need to do a u substitution with the x plus 2 under the root, but I don't want to do a u substitution with the second term that is x. When I set up my u sub, I want it to be x plus 2 That makes du dx equal 1, so du and dx are equal. But mind you, I'm only doing it on this integral, not the other one. So this integral turns into the square root of u times, replace the dx with du. Then my x values of 0 to 2, using the equation that was chosen for relationship of x and u. When x is 0, y is 0 plus 2, or 2. When x is 2, y is 0, or y is 2 plus 2, which is 4. And the other integral I'm going to leave as it is. Integrating root u means u to the 3/2 times 2/3, evaluated from u equals 2 to u equals 4. When I plug in the 4, I square root it to 2 and then cube it to 8. When I plug in 2, it's not pretty. It becomes 2 root 2. I guess it's not that ugly, but anyway. Then, moving on to this piece, the integral is x squared over 2 from 0 to 2. That gives me, when I plug 2 in, I'm going to get 4 divided by 2, which is 2. When I plug in 0, I'm going to get 0. Then you can do the arithmetic to simplify that, and then use exactly the same procedures to integrate this other function, but from 2 to 4. So you'll have to separate them and u sub this one that I'm pointing to, leave the other one as it is. All right. 35, which is the last one. That was a calculator problem. And with this calculator problem, you needed to draw the graphs on your computer. I preset, I drew this on Desmos, found the intersection, and then pointed that out. If you need help with your calculator, ask me about it, because that's becoming more of an individual issue. So the red function that you see is the first one, the x times the sine of x squared. The blue function is the y equals x to the 4th. And I'm only looking for when x is greater than or equal to 0. They intersect at 0, and they intersect at the x coordinate 0.896. If I want to find the area, then drawing vertical lines between them, maybe I should use another color, there we go. I can see who is making y top, who is making y bottom. And when I draw vertical lines, that means the infinitesimally thin dimension is x. I am integrating with respect to x from x equals 0 to x equals the intersection point of 0.896. And its length times dx. The length is y top minus y bottom. And then at this point, you can put that in your calculator and allow your calculator to solve that integral for you. And I'm going to leave it there. If you have any more questions, make sure you ask me, and I will see you later. Bye.